Okay.
No.
Right,
the floor is yours.
Thank you. Thanks to the organizers for inviting me. Yeah, I'm excited to talk about this work. This is pretty different from the last, whatever I talked about like a year, or I guess it was 2 years ago. So yeah, this work is on the archive, and it's joint work with Anton Dochtermann, who's at Texas State, and Ben Smith, who's at Manchester. So, I mean, this is just a very short outline. I mean, the story is I'm going to tell you a little bit about tropical hyperplane arrangements. I think some people in this group might be more familiar with this story than others. I'm going to talk about different ideals that you can get from arrangements and free resolutions that you can get from looking at the tropical hyperplane arrangements of those ideals. And then I'm going to talk about applications to toric edge ideals of bipartite graphs. Okay. And so to start this story, so when I'm in the max tropical semi-ring for the duration of this talk, unless I say something otherwise. So I'm taking max as my sum here. And so, tropical polynomials make sense. And, if you have a tropical polynomial, you can view it as a piecewise linear function, right? By taking the max of all of these pieces, right? In this way. Probably, again, some of you have seen this. Probably many of you know this story. And so addition and scalar multiplication make sense for vectors, right? And so one thing to notice that when you do scalar multiplication, what you end up doing is really you're just kind of adding a scalar multiple of the vector to of the all ones vector to your original vector, right? And so this is why often we're going to identify a tropical linear space with its image in the tropical torus, where we like mod out by this lineality space. Okay, this is going to be homomorphic to R to the d minus 1, and this is where I'm going to draw all of my pictures for the duration of this talk. Okay. And so the only tropical curve that I'm really going to be talking about in this talk are tropical planes. Many of you are probably familiar with tropical hyperplanes that look like this, right? And so I specify an apex, and in order to define a tropical curve, you're looking at the curve, and you're looking for the places where the max is attained twice. Okay, so what does this mean for the people not familiar with this? So here at 0, 0, 0, the max is 0 and it's attained in all of the positions. Now here, where x is negative and y and z are equal, in this case they're equal to 0. If x is negative and y and z are equal to 0, then the max is attained twice. So I get this ray going in this direction. And remember that I'm modding out by this lineality space. So this sort of accounts for any spot where y and z are equal and x is less than them. This, let's say that this is the z-axis, let's say this is the negative z direction, then the max would be achieved twice by the x and y, because z is negative, and then this would be the negative y, so x and z attain the max twice, right? So this is why this is what our hyperplanes look like. But one thing that I'm talking about today that's a little bit different than what maybe some of you have seen before is I'm going to allow for coordinates of my apex to be at infinity. And so what do I mean by this? So here I took this in the x direction towards infinity. So you can imagine that the apex is way out here somewhere. And but the max is still going to be achieved twice. Well, okay. Sorry. So this should be, maybe I should have said that this was negative infinity, and I should have drawn it going the other way. No. Okay. Sorry, now I'm getting all flustered. But okay, the point is you can kind of take your apex to infinity, and then you see what your ray looks like from there, okay? And so this is what is left of the hyperplane after I pull my apex all the way this way, right? Oh, right, yeah, it's right, that's right. I'm taking negatives of the apices. So if I have an infinity here, then I have a negative a1. So the max is attained twice by the y and the z. That's right, okay. And so we can encode an arrangement of tropical hyperplanes by this tropical matrix, right? So each column is going to specify one of the apices. And again, I'm allowing for the case where some of these apices might have indices at infinity. And so my picture might look like this, for instance. Here's an example of the kind of tropical hyperplanes arrangements that I'm going to be talking about today. And so one key idea is I'm going to be talking a lot today about the support of tropical hyperplanes. So here in this picture, this is the typical tropical hyperplane that you might be used to, and these have full support. So all of the entries of the vector that are indicating my apex are finite numbers, okay? But if I pull the apex to infinity in any of the directions, then I get something that does not have full support. So in this case, the support is 1 and 2. Because I have the sectors that correspond to x being the max, and I have the sector where y is the max. So that's why these are the support. And so I'm going to label, I haven't defined what these sectors are yet, but that's how I'm going to label each of these sectors. And the support is going to be sort of the sectors that are left after I pull things in a direction towards infinity. And so we can encode the support of the whole arrangement by a bipartite graph in this way, right? And so on the left-hand side, I have the number of sectors. On the left-hand side, I have the number of sectors. And on the right-hand side, I have one vertex for each of the hyperplanes. And I'm just going to indicate the support by connecting the vertex corresponding to that hyperplane to the ones corresponding to the support, right? So 1 has full support, so it's degree 3. 2 has support 1 and 2. 3 has support 2 and 3, and so on, okay? So I can encode the support by this bipartite graph, okay? And so tropical hyperplanes with full support have been really well studied. There's a really deep theory that connects tropical hyperplanes to all kinds of different objects and combinatorics. For instance, it's taking a minute to load, but the one that you can see so far is the tropical hyperplane arrangements with full support are dual to mixed subdivisions of dilated simplices, right? And so you can see here, I mean, for each apex, I take now each apex is now going to correspond to a maximal face. The maximal faces of the arrangement, like the way that I cut up the tropical torus, are now going to correspond to vertices. Edges correspond to the rays, and so on. I end up getting this mixed subdivision of a dilated simplex, and this was first observed by Develin-Sturmfels. And via the Cayley trick, actually, this is also related to a regular triangulation of a product of simplices. And I'll talk a little bit more about the Cayley trick later. Okay.
Can I ask a question?
Yeah.
Do we consider tropical hyperplanes only in 2 dimensions, or?
Oh, I'm considering them in any number of dimensions, and in general, they'll kind of look like the rays that would define like a more general simplex. But I am only drawing my pictures. I can't draw it in higher dimensions, but you can play with polymake to see what they look like in higher dimensions.
It's a normal fan of the simplex.
Yeah, the normal fan. Sorry, thank you. It would be the normal fan of a simplex more generally. These are just the pictures I could draw. But you can study more general arrangements by putting them in polymake, for instance.
We consider in this hyperplane arrangement that all tropical hyperplanes of the same dimension.
Yeah, they're all the same dimension. That's right. Yeah. That way we can encode it in a matrix. Okay, good. And so, right, okay. And so via the Cayley trick, we can go back and forth between triangulations of products of simplices and fine mixed subdivisions of a dilated simplex. I cite Santos here. I mean, this goes back actually to work of Sturmfels even earlier than that, but there's a nice paper by Santos where he summarizes this for this particular case. And then this regular triangulation is a simplicial complex, right? And so this is going to correspond to some monomial ideal. And in particular, the monomial ideal that it corresponds to is the initial ideal of the 2x2 minors of this D by N matrix, right? Where here D and N are going to be the dimensions of my tropical matrix. Actually, for this, I should have also written down what the tropical matrix was for this particular example. And in turn, that is the initial ideal that you're picking actually is corresponding to weights that are defined by your tropical matrix. And so this is sort of the summary in the full support case. I'm going to talk a little bit more depth throughout the talk about all of these pieces, especially in this more general case where we're allowing the hyperplanes to be pulled towards infinity in different directions. Okay. And so to start, I have to tell you a little bit about fine types and tropical covectors. So yeah, I kind of hinted at this earlier. We're going to take the ith closed sector to be sort of the piece where the aith spot, when you shift by that point, is greater than or equal to the ajth spot. So in general, the way that you can think about it is that here x is the max, is the only thing that achieves the max. Here y is the only thing that achieves the max. Z is the only thing that achieves the max. And that's the way that that's the easiest way, I think, to remember it. And so the fine types are, and these are also called tropical covectors, kind of an analogy with just classical oriented matroids. But I'm going to have types and cotypes. And types aren't really vectors of a matroid. So I'm going to avoid using the covector terminology. I'm going to use the type terminology here. So fine types are going to record which side of which hyperplanes your points lie on. And so,
can you remind how many hyperplanes do we consider in the arrangement? We can
just however many columns of your matrix there are, that's going to be the number of hyperplanes. So this example had 4 hyperplanes, so it had 4 columns, and then there are 3 possible sectors, so it had 3 rows for each sector. And so I had this example above. And so the fine types are recording which side of which hyperplane each point is on. Okay, so for instance, this yellow cell has this fine type. So I'm recording, again, the right side is the hyperplanes, and I'm recording which sector of which hyperplane I'm in. So V1 is on, it's in, so here I have a little compass for you. And so we're on side, so hyperplane 1 is the blue one. So we're on sector 2 of hyperplane 1. For hyperplane 2, we're in sector 2. For hyperplane 3, we're in sector 3. Hyperplane 3, sector 3, we're under here. And hyperplane 4, we're in sector 1. Yeah. And so we can encode this in 2 different ways. You can encode it with this bipartite graph like this, or you can encode it in a monomial like this. You could also encode it in a table if you want. And the table way is nice for proving things, but for the sake of this talk, it's nice to view it in either of these ways. And you can also, for instance, this cell, this ray right here is going to, for instance, is on both, it's in sectors 1 and 2 of hyperplane 1. So you can see that here hyperplane 1 has degree 2. Okay, and so the smaller dimensional cells are going to correspond to, you're going to have higher degree things on the right side, or higher degree corresponding monomials. And so, yeah, these monomials, just to make sure that we're reading it correctly, the left index is the right side of the bipartite graph, and the right index is the left side of the bipartite graph. So it's actually flipped from this picture. But okay. And you can consider the coarse type instead. The coarse type is just the left degree vector of the corresponding bipartite graph for the fine type. So it's like you're only remembering, how many hyperplanes am I on side 1 of, how many hyperplanes am I on side 2 of, how many hyperplanes am I on side 3 of, right? So here the course type is 1, 2, 1, or you could just think of it as this monomial, right? So the fine type will always be like a square free monomial, but the course type, it kind of collapses in some ways, right? It's like now you're only remembering the first index. So I get 2 things that correspond to x2. Yeah, so code all possible fine and course types by ideals by remembering the fine and course types of all of the cells in the arrangement, right? And so notice, I had mentioned that we only, that the bigger the cell, the smaller the monomial, right? The smaller the degree of the monomial. And so really you just have to remember if you want to think of it as an ideal, you just have to really remember the generators are going, the minimal generators are going to correspond to the monomials for the bigger cells out here, right? And so this, if you look at the dual of this picture, you're going to see that this is what the picture looks like. And I labeled the vertices in the dual picture with the course types, where I wrote them as just degree vectors. And so you can see that we are getting a mixed subdivision of something in this picture, right? And so there is like an analogous story to what we saw earlier. We saw that if you had hyperplane arrangements with full support, then the dual picture corresponded to a fine mixed subdivision of a dilated simplex. So we're getting something more general here. And what that more general thing is it's actually a permutohedron. And so actually, in particular, we're getting a generalized permutohedron, right? So some edges in higher dimensional bases can be degenerated. So we're going to have this generalized permutohedron in general. Sorry that now there's going to be more on the page at the same time, but it's okay. For instance, here is just the usual permutohedron for n equals 3. You can deform it into a dilated simplex, and then you could deform that further into this picture. And so you could see how you could do a similar kind of deformation to get this generalized permutohedron, which is what we got, before. And in particular, Minkowski sums of simplices are always generalized permutohedra. And so actually we can describe the generalized permutohedron we get in terms of sums of simplices where the sizes of the simplices are determined by the size of the supports. Okay. And so in this running example, this was the bipartite graph that gave us the support of all of the hyperplanes. And so you see, the first thing was degree 3. So I get just the full simplex here. This one was degree 2, so I just get the line segment, line segment, line segment. And the directions of the line segments are going to correspond to which sectors are in the support. And when I take that Minkowski sum, I'm going to get this picture. And so it's interesting because this picture, I had no information whatsoever about what the arrangement actually looked like or where, each of the hyperplanes was placed relative to each other. But the point is that if I place the hyperplanes in a sufficiently generic way, when I take the dual, I'll get a subdivision of this generalized permutohedron. Okay, and this is work of Fink and Rincón. That's where this story comes from. So I say it here. And so, oops. So if you're given a tropical D by N matrix with this support graph G, then the tropical complex is dual to a mixed subdivision of that generalized permutohedron. That comes from taking the sums of simplices in the way I described right here. And so what we were able to show is actually this mixed subdivision does more. It actually supports a minimal linear cellular free resolution of the fine and coarse type ideal. And I'm going to sort of focus on the combinatorics a little bit in the first half, and then I'm going to talk a little bit more about free resolutions in the second half of the talk. I just thought I would mention this now. So if you know what a Betti table is, then and even if you don't, you'll notice that the 11 is corresponding to the 11 vertices, the 16 is corresponding to the 16 edges, and the 6 is corresponding to the 6 faces right here, right? And so I'll talk a little bit more about cellular resolutions in more depth later. So how does the tropical matrix determine the subdivision? Well, one way to see this is it actually determines a regular triangulation of the root polytope associated to the bipartite graph G. So root polytopes were introduced by Postnikov, and then the Cayley trick is going to determine a subdivision of the corresponding generalized permutohedron. And so let me summarize the story up here first. Oops. Sorry. Okay, it's fine. Okay. So yeah, I was just summarizing the story up here. So this is the summary. So I have a tropical matrix. I get a triangulation of QG by kind of raising the vertices to the heights in my tropical matrix. And then I can use the Cayley trick to get a subdivision of the corresponding generalized permutohedron. And the dual of that is going to correspond to the tropical hyperplane arrangement, which in turn is also given by this tropical matrix A. So this is sort of a summary of where we're heading. And so for those who aren't familiar, a root polytope, so okay, there are multiple definitions of root polytopes out there. I'm actually talking about a specific class of root polytopes here, where I have a bipartite graph. Well, I'm only focusing on the case where G is a bipartite graph. And so I'm gonna have unit vectors that are gonna correspond to, so I'm gonna be an RD plus N, where D was the number of rows and N was the number of columns, or vice versa. No, D was the number of rows and N was the number of columns. And so here in this example, I have a bipartite graph and it's going to correspond to this root polytope. So I'm taking the EI minus EJ such that IJ bar is in the edge set. So I'm viewing these right-hand ones as barred, kind of. And so this 1, 1 corresponds to this vertex right here, which would be E1 minus E1 bar, E3 minus E1 bar, and so on. So I get this nice little Toblerone picture, this little prism. And you can get a regular triangulation of a root polytope from the tropical matrix in the following way that I kind of described up here. So this is sort of just a small example because I could draw this example. So here, if this was my tropical matrix, this is the bipartite graph, you just get the complete bipartite graph K22. And so I'm going to get a triangulation of this little square. And so what I'm going to do is I'm going to raise each vertex. I'm going to kind of imagine that I add another coordinate and then I can raise each vertex to the corresponding coordinate, right? So the 1, 1 vertex is just raised 0. The 1, 2, 1 vertex is raised 0 and so on. But the 1, 2 vertex is raised by 1. So I'm going to raise it and then I'm going to project down what I get. And so what I end up getting is when I project the faces down, I end up just getting this triangulation right here, right? And so the Cayley trick is going to take triangulations of the root polytope to subdivisions of this generalized permutohedron, right? And so, you know, I'm only talking about this in this particular case where we're dealing with products of simplices and, we're dealing with root polytopes and generalized permutohedra. But in this case, this is what the story looks like. Is you are taking a face of the triangulation and it's kind of going to a face of the subdivision. And so in this example here, I have this triangulation. I have this simplex right here and here, right? X1, 1, and then the others are all 1, 2, 2, 2, and 3, 2. Well, that's the Cartesian product of these two things. And what the Cayley trick kind of does is it takes this Cartesian product and it takes it to a Minkowski sum. This is very informal, but this is just sort of the way that you can think about this picture. And so now I'm going to get this, this face right here, and that's going to be this one right here. And then similarly, I can decompose each of these triangles into a Cartesian product of things, and those are going to translate to Minkowski sums of things over here in this subdivision picture. And so that's kind of how the Cayley trick works in this case. And so the Stanley-Reisner ideals of regular triangulations are going to correspond to square-free initial ideals of the corresponding lattice ideal. Okay, so what do I mean here? So again, the regular triangulation is just a simplicial complex. It corresponds to some ideal, some square-free monomial ideal by the Stanley-Reisner correspondence. And what Sturmfels showed in the early 90s is that you can see this this triangulation as coming from an initial ideal of the toric ideal that defines your lattice polytope. Okay, and so in this case, when I have a root polytope, unfortunately these ended up on different pages after I turned it into a PDF, but I'm taking the kernel of this map where I'm sending sort of the variable that corresponds to a point. So here it would be like x32 or something. And I'm sending it now to like two different variables, like x3, y2 is what's happening in this picture. And so, well, yeah, and I have to, so I'm taking ei minus ej bar, but it doesn't really matter if I'm using inverses or not, because all the inverses are on the same variable. So we'll just say xi, yj. And so if G is the complete bipartite graph, I'm getting exactly the 2 by 2 minors of a D by N matrix, right? This will just be the Segre embedding if I do that. And so more generally here, if I have this tropical matrix, I can assign a weight aij to each of the variables, right? And that's exactly what the tropical matrix is doing. And I'm going to just ignore the variables that have infinities, right? It's like those variables don't show up, right? I don't have an edge in the bipartite graph corresponding to these spots with infinity. So I don't have a variable corresponding to them. I can just ignore them. And the ones that are left, I'm going to give weights that are going to correspond to the weights in the matrix. And yeah, so now, for instance, in this example, I take this corresponding initial ideal. So the weights are, like I said, are going to correspond to what I see here. So here, x11, x22, 11, 22, the sum of zeros and 0 is 0. But x1, 2, and 2, 1, that's this diagonal, 3 and 0, that sums to 3. So this term wins. So this is going to be the leading term of this binomial. And you can play this game and calculate what the winner is going to be. And in general, if my arrangement is sufficiently generic, like I don't have any rays on top of each other or anything like that, I will get an honest monomial ideal. This story works if the arrangement's not generic and you have maybe things on top of things, but it might be that terms are tied. But I'm just gonna, for the purposes of this talk, I'm gonna avoid a lot of these nuances and just focus on the cases where things are sufficiently generic because the story is particularly nice. And so, so in conclusion, this is going to be the Stanley-Reisner ideal that it corresponds to the triangulation that you get from this matrix. Okay. So the combinatorial way is you think about raising the heights and then projecting back down, but the sort of algebraic way to compute the triangulation is by taking the Stanley-Reisner ideal. Is by taking this initial ideal and looking at the associated simplicial complex. Okay. And so the Alexander dual of this initial ideal is actually going to encode information about the arrangement. And that's going to correspond to the defined cotype ideal. And so I have to point at this picture. And so in this picture, the bounded complex of the arrangement is going to give a cellular resolution of this cotype ideal. So how does this cotype ideal work? So I talked about the fine type ideal where I was kind of just labeling which side of which hyperplane I was on. The cotype ideal does the opposite. It's like the complement monomial, or you can think of it like Instead, now I'm looking at which sides of which hyperplanes am I not on, right? So like this point right here, I am not on sides, sectors. I think these are 2 and 3 of hyperplane 1. And so, sorry, it's 1 and 3 of hyperplane 1. So I get an x1, 1 and x3, 1. And then I'm on both sides of hyperplane 4. I'm on both sides of hyperplane 3. But then hyperplane 2, I am on side 3. So I am on side 1. So I am not on side 2. So that's why I get this x1. Sorry, I said it backwards. x1, 2. So I am not on side 1 of hyperplane 2. So anyway, this gets confusing because it's a little bit backwards. But the point is that you can find this cotype ideal in the same way, and it'll be flipped. Right now, the smallest degree monomials are going to correspond to the smallest cells. So here they're going to correspond to the vertices of this bounded complex, actually. And this bounded complex is actually going to give me a cellular resolution, which I'll talk about a little bit more after the break, of this fine cotype ideal. Okay. And so again, even if you're not familiar with resolutions, you can see that this homological information about the ideal is going to correspond to information about this bounded complex. So here I had 6 vertices, 7 edges, and I have 2 of these 2 faces. Yeah. And so just a summary of all of the things, all of the pieces of this story today are, if you're given a tropical hyperplane arrangement, it corresponds to all of these things, right? You have this bounded complex right here. So those are just the bounded cells. That is going to be a free resolution of this fine or coarse cotype ideal. The Alexander dual of that is going to be the initial ideal of that lattice ideal that corresponds to the root polytope associated to G. Stanley-Reisner theory takes me from that initial ideal to a triangulation of the root polytope. The Cayley trick takes me from the triangulation of that root polytope to a fine mixed subdivision of a generalized permutohedron. And that generalized permutohedron, the subdivision that I get from that actually supports a free resolution of the fine type ideal. And so I have all of these different objects that are all related to each other in these ways. So yeah, maybe we can take a little break at this time and people can ask questions or whatever, go take a little break. And then I can finish the second part after. Okay, so for the second part, I'm going to talk about sort of homological information that we can get from this story and other ways that we can view these ideals. But first, I mean, again, like I feel like this group has a very diverse, everyone comes from very different backgrounds. And so I'm going to do a little mini crash course on free resolutions. I think some people are going to be more familiar with this story than others. And so, yeah, so the key idea here, so this was introduced by Hilbert in 1890 or so. And the way that you can think about it is the following. Like if you are given a module and you're like, I want to understand the structure of this module, right? So for a vector space, it's sufficient to just give the basis, right? But for a module, if you just have the generating set, that doesn't really, you can't detect any deeper information about the module from just having the generating set. And so the way that you can think about it is like the generating set, if you think about like the free module that has a basis that corresponds to that generating set, that's kind of like a first approximation of your module, right? But you might want a better approximation than that. And so then what you can do is you can look at the relations on the generators of the module and then, make a free module out of that whose basis now corresponds to those relations. And then keep going like that. And you can assemble them into a complex in this way. And you can really think about it like at each step, you're approximating your module better and better. Okay. And so Hilbert's syzygy theorem tells us that you can do this. You can, assemble these free modules into an exact complex in this way. And if you're working over a polynomial ring, this will end, this will terminate. In general, these might be infinite, right? If I'm working over a quotient ring or something, or like the exterior algebra even, like these can be infinite. well, not the exterior algebra, but if I'm working over like an Orlik-Solomon algebra or something like that, these could be infinite. But if I'm just working over a polynomial ring, I'm good. Everything is good. Okay. And so, right. And so, so I say that a free resolution is minimal if there are no units. So you can think these guys are matrices, right? And the fact that this is a complex, I'm saying that if I take two consecutive matrices and I compose them, I should get 0. And I say that the free resolution is minimal if there are no units that show up in the matrix, right? Like I should only get, I can get zeros, and then otherwise I should just get, things, non-units in my ring. And so if I'm in a polynomial ring, they should be polynomials, right? And so since the minimal free resolution is unique up to isomorphism, I can express the information given by a free resolution, or some of the information given by it, using a Betti table. And so, okay, so yeah, you can kind of see in these pictures. So I'm going to have like a degree shift. This is just because I want my maps to be degree preserving. And so that's what these minus J's are. And I kind of want to keep track of the ranks of the free modules that show up here. So the ranks of those graded pieces. And so beta's, this homological degree 0, 1, and so on. And so the homological degree is the first index, and the second index tells me the degree of the object. And so, or the degree shift that I had to do. And so when I assemble these into a table, notice that, because these maps, I don't want any units in the matrices, they're, I have to shift by a positive degree at each step. And so it's kind of, so this is why this indexing is a little funny. If you've never seen Betti tables before, I'm gonna, in the ijth spot, I'm gonna put beta I plus j, because everything below, I'm kind of getting rid of a diagonal, this big triangle of zeros I would have if I were to just put I. Okay. And so this is just kind of a more efficient way of encoding this information. And so if the free resolution is finite, then the number of steps is going to be the projective dimension. That's what I'm going to call this. And the regularity is going to be, so the projective dimension in this table is going to be the width of the Betti table, will be the number of columns. And the number of rows is going to correspond to the regularity, which is kind of encoding like how big are the degrees, how big are the degrees that show up in my maps of the polynomials that show up in the matrices of these maps, right? And so what's even nicer is if you're working with monomial ideal, I referenced earlier that I got cellular resolutions. If I'm working with a monomial ideal, then sometimes it happens that your resolution is supported on the chain complex of a regular cell complex. And so this is just kind of a small example to see how this might happen. So here I'm just taking the second power of the maximal ideal in 3 variables. And so, I take this particular free resolution with this particular choice of maps, and it's actually going to correspond to this picture where if you what you imagine is you kind of imagine that if you got rid of all the variables and you just had like 1s and -1s in the matrices, and then replace this with like, the field k to the 6th, k to the 8th, and so on, you would get the actual chain complex for this cell complex without the monomial labelings. So that's kind of the intuition. And so here, but we do have the monomial labelings, and if you want to prove that something is a cell complex, you have to show that these monomial are consistent in some way. So in this small example, I labeled sort of the degrees of each of the generators of each of the free modules, right? So here, so the generators are going to correspond to the basis elements of this free module. So those are the vertices at the first step. And so I get 6 vertices. At the next step, I get 8 minimal relations between them, and those are going to correspond to these edges. And so you'll notice, for instance, that like this edge that I'm missing between xy and yz is redundant because I can write it as a linear combination of the relations that I get from xy and xz and xz to yz. So I don't need that one. So I get 8 of these edges, and And so, yeah, just to show you this x squared y, for instance, that's the degree of this relation, where if I took y times x squared and I subtracted x times xy, that's equal to 0. So that the total, like the fine degree would be x squared y, or like 1, sorry, it would be 2, 1, 0. 2 in the first index, 1 in the second index, and there's no z in here. And moreover, this resolution is linear. So it's called linear because everything is just in a line in the Betti table. And it also means that all of the matrices after the generators, all of the matrices that show up just have linear entries. Okay, and so this is a particularly nice resolution. And so yeah, having a cellular resolution is just really nice. Yeah, it just allowed us to encode the information about the ideal in a nice, satisfying way. And so I had mentioned earlier that the bounded complex of my arrangement, so we proved this, me and Anton and Ben, the fine cotype ideal of the arrangement had a minimal cellular resolution given by the bounded complex of the arrangement, right? Where again, I'm just looking at the bounded cells. That's what it sounds like. And moreover, this resolution it's a linear resolution. So the degrees only go up by 1 when I go from one-dimensional phase to the next. It's a minimal resolution. I don't have any redundant information from looking at this picture. Yeah. And so in particular, notice that the length of the free resolution, the projective dimension, is going to be 1 more than the dimension of the bounded complex. Okay. And so, yeah. So the idea is we can kind of understand the projective dimension of the fine cotype ideal by understanding the dimension of the bounded complex. Okay. So, yeah, so the other key thing is that the projective dimension of a monomial ideal is always going to be equal to the regularity of the Alexander dual of that monomial ideal. I think this was first observed by Toric. And so understanding the dimension of the bounded complex tells us about the regularity of whatever the Alexander dual of this cotype ideal is. And so I had interpreted you might remember earlier, I had interpreted the cotype ideal as coming from being the Alexander dual of this initial ideal, of this toric ideal corresponding to the root polytope. But there's another way that you can interpret that ideal, and it's as a toric edge ideal. And so you'll look at this definition and you're like, wait, this is just the same as the definition of the lattice ideal for the root polytope, and that's true. So yeah, here we're just sending an edge in. So this, if you're given a graph G, you take an edge of the graph and you're going to send it to the product of, well, you're going to send it now to this ring where now you're going to have your variables corresponding to the vertices. And so you're going to take an edge here and you're going to map it to this quadratic thing that is going to correspond to the two vertices that your edge is connecting, right? And so indeed that is, so yeah, this is a very well-studied class of ideals in commutative algebra. There are a lot of people who have been studying these things, trying to bound like how bad these homological invariants, like the projective dimension and the regularity, can be. I think that's something I forgot to mention when I was talking about regularity and projective dimension is, you know, sometimes it's really hard to actually get your hands on like what the resolution looks like, especially like understanding the maps. But if you have a, you know, sometimes what you can do is you can still like say how complicated your ideal or module is by giving information about how bad the projective dimension or the regularity can be. Okay. And so often these are both kind of viewed as like measures of how complex your ring or module are, right? And so, yeah, so in particular, if you're given a bipartite graph, you can now view sorry, I should have put initial ideal up here. So yeah, you have two ideals that you can associate to it now. You can associate this toric edge ideal for the graph. Sorry, these are the same. So there's the toric edge ideal for the graph, and then there's the lattice ideal for the root polytope associated to G, right? And moreover, this is one particularly special property is the root polytope is unimodular. That means that if you look at the matrix that, you're taking the convex hull of a bunch of EIs minus EJs, right? And so if you look at that matrix, it means that if you take any size minor of that matrix, the determinant is 0 or plus or minus 1. And so this is a particularly nice class of lattice polytopes where every initial ideal is going to be square free. What ends up happening is that every triangulation is going to correspond to an initial ideal, and there's going to be bijection between them. So this is a particularly nice case of things. And the other thing is, if you have a square free initial ideal of any ideal, a recent result of Conca and Barbaro showed that the regularity is the same, and so is the projective dimension. And so if you have an ideal, you take the initial ideal. If it's square free, the regularity and the projective dimension are exactly the same on the nose. And so here's, of course, my schematic got split into 2 pages, but here's kind of the story is we're given a graph G, and we want to understand its toric edge ideal. Well, we can pick any sufficiently generic tropical matrix, and that's going to correspond to some arrangement. And that is also going to correspond to some initial ideal of your toric edge ideal, right? And so what you can do is by Alexander duality, now you can study the fine cotype ideal associated to that arrangement. And then when you look at that fine cotype ideal, the bounded complex is going to be the minimal free resolution of that cotype ideal. And so if you study the bounded complex, now you suddenly have homological information about the toric edge ideal. And so this is kind of the trajectory that we're taking. And so, the first theorem, as I kind of said this already, is that you can prove that the regularity of, if A is a sufficiently generic arrangement, then the regularity of the toric edge ideal associated to G is exactly the dimension of the bounded complex, right? And that's by, again, following this schematic, because it's like you take this initial ideal, it's the same. Okay, well, you resolve the Alexander dual of that, that the projective dimension of that is equal to the regularity of the Alexander dual. And so that's sort of how you follow this along. And so we introduced this new tool to study the dimension of the bounded complex called the recession connectivity of G. I'm not going to get into this because it's kind of technical, but you can look at the paper. But the point is that with this recession connectivity invariant of a bipartite graph, you can actually exactly compute the dimension of the bounded complex. And so, for instance, we're able to use this to both recover and strengthen a lot of bounds that were in the literature about regularity of bipartite graphs. For instance, the recession connectivity is bounded above by the matching number of the graph, okay? And so this actually implies a result of Herzog and Hebe that they actually took a lot of work to prove. For us, it ends up being kind of just a corollary. Which is pretty nice. And similarly, we can also give, that story tells us about regularity, and we got other bounds too that are kind of annoying to state, so I didn't put them in this talk. But actually we recover and strengthen a lot of other bounds in the literature that give bounds on the regularity in terms of other invariants of the graph. And so another thing that we're able to use this for is we give a new proof characterizing when toric edge ideals of bipartite graphs have linear resolution. And so this actually was something that was open for a surprisingly long time. And Akioshi Tsuchiya just posted a proof last year. And like I said, his proof, it's sort of similar to this story up here, where his proof actually like was pretty technical and took a lot of work. And we end up just getting it as a corollary. And so again, G is, if G, you have some connected bipartite graph G, then it has 2 linear resolutions. That means that all the generators are quadratic and it has linear resolution. If and only if it's obtained from adding trees to the bipartite graph K2D. So if you take the complete bipartite graph and just add some trees to it with no cycles, you'll get a linear resolution. And that's the only way you can if you want the generators to be degree 2. And more generally, if you want the generators to be of higher degree and you want it to have linear resolution, the only way that it'll happen is if it's a hypersurface. And so, yeah. And so this is something, again, that just kind of falls out of our work, but is really nice. And so, yeah, that's actually all I have to say. I probably talked too fast at the beginning after my technical issues, but thank you for listening.
Thank you so much for the talk. So
Yes, thank you very much.
Yes, let's thank the speaker, but yes, everyone is doing this. Anyway, are there any questions from the audience?
Can you repeat what does loops in bipartite graph
Are you asking about, did you say loops or cycles in the graph? Is that what you were asking?
cycles?
Yeah. So yeah, I didn't really get into this, but if you want to describe the generators of a toric edge ideal / the lattice ideal of a root polytope, what it comes down to actually is studying, I don't have an example in here actually, well, maybe I'll go to an earlier example, but it comes down to is studying the minimal cycles. And so here, for instance, here I have, yeah, so I didn't write down what the corresponding ideal is, but this one is just going to be a hypersurface. I'm just going to have a single generator for the toric ideal. It's going to be, and it's going to correspond to x11 minus, or sorry, x11 times x22 minus x12 x21. So it'll be exactly the just the determinant of that generic matrix, the little 2x2 generic matrix. And so yeah, you can always get the minimal generators by looking at minimal cycles of your bipartite graph, and then sort of taking every other thing, every other variable, and then sticking it into a monomial. And so I do x11 goes into the first monomial, x12 is going to go into the second monomial, x22 goes into the first monomial, x12 goes into the second monomial, for instance. And so more generally, if I had a bigger cycle, then I'm going to get a higher degree thing. It's still going to be 2 terms, it's still toric, but you're going to get a higher degree thing. So if I had a 6 cycle, then it would be degree 3, for instance. And you take every other one and put it in each monomial. And so yeah, you only have to look at the minimal cycles to get the generating set.
Does that answer your question, Vladislav?
Sorry, so considering minimal cycles, we can build generators of toric ideals.
That's right, yeah.
Okay.
Okay, any other questions? If not, I'll stop the recording.